Welcome back to my channel. Let us today discuss a very interesting concept regarding counting. So I am now talking about only basics of counting. Okay, we are just learning from the start of counting. Okay, suppose I say I have 5 objects A, B, C, D, E. A, B, C, D, E. And I want to select from these 3 objects. So we are talking about selections now. Selections. These selections of 3 objects from 5 objects. So what I am talking about, I want the selections of 3 objects from 5 objects. Let us list some of the selections. Number 1, I will select A, B and C. Whether I write a comma in between them or a dash in between them or continuously I write A, B, C, that all means the same. So a better notation is to use set notation. A, B, C. When we write these brackets, order is not important. You write B first, A first, next then C, that is one and the same. So generally in sets, position is not important. And we are not going to do repetitions. We are never going to write A, B, B, C. That all finally reduces to ABC. And CAB means the same thing. So I am talking about this set containing 3 objects from these 5 objects. This is S1, let us say. Now I am writing second selection. I am taking A, comma, I am taking B, comma, I am taking E. So what is the set corresponding to this? S2 is equal to A, comma, D, comma, E. So on. The question comes, how many such selections will be there? On the whole, if I go on counting like this, some K will be there here. That K is how much in the list? That's my question. So it is SK suppose. Some box here, some box, some box. 3 elements will come, 3 objects will come from these 5 objects. Can you make a guess how many will be such selections? 2 options now. 2 ways are there. Write all this and then select and then see how many are there. You count it. But this is not the good way, not the proper way, because here it is 5 and we are selecting 3. It is a small list, you will get it. But if I say you are allowed to use all A to Z 26 capital letters and you are selecting 13 of them or 10 of them, then these 10 objects are selected. From 26 objects, how many such selections will be there? If you go on writing on paper, then a stage will come where the paper ends. You will go to another paper and then you don't know what selections are already written and what selections are remaining. So that is really a headache. If I say that, no, if you say that my memory is good, I will remember all those pages, I will say I am selecting 1000 objects. You may say, how 1000 only A to Z? No, I will say A1, A2, A3. So on up to A 1 lakh. 5 zeros will come in 1 lakh, okay. And I am selecting 233 from them, 233 objects. It's definitely a matter that, okay, fine. Thank you, sir, thank you. Let it be, no problem, let it be. So A1 into A3 so on up to A1, 1 lakh. I am selecting 233 objects from this one. It is not so easy to count how many are there. So what is the better way? The better way is to introduce a terminology. What is that terminology? Now, shall I wrap this one? You got the concept? Let us talk and exactly let us see in the case when there are 5 objects and 3 objects, so that That same concept can be applied to any number of objects n here. Let us say n is the total number of objects. Total number of objects, and this is R. This is n and this is R. Objects we are selecting. So we will use this notation of n and R. I hope you are following, right? Good. So simple concept. If you have n objects, totally R objects are selected. This is total. Selected R objects. Then the total number of such selections. Each selection we are going to introduce a term called combination. Combination. This word combination is a new term appearing in the basics of counting. In all counting problems, whenever I say combination, I mean a selection where position is not important, and this combination is taken of R objects from n objects, that is denoted by NCR. This is equal to total number of selections of R objects from n objects. So this is only a notation. The question comes, how much will be the value? Then I will tell two things very clearly. What is notation? What is the way to calculate that one? With a simple example. Suppose I have 4. I am multiplying with 4. I am multiplying with 4. Then so on up to 4. This is 1000 times. Then what is the way to write? The way to write is go on writing 4 up to 1000 times. What is the beautiful notation of this one? So simple. You will just write base as 4 and you will write the power as 1000. This is the notation. I am not asking about the value. If you want the value, you have to multiply 4000 times and you have to get it. So that value is not required now. If you multiply 4000 times, then the notation is 4 to the power of 1000. Exactly similar. This is the value, this is the notation, this is the value. Value is not required right now. We are not calculating that one. So this is notation, this is the value. Here I was talking about totally how many objects? A, B, C, D, E. There are 5 objects. And one such selection we have written A, B, C. And there are 3 objects. 3 objects. So how many selections will come? This is written here. These selections we are going to call as combinations. In the terminology of counting, it is combination. There is one more called permutation, where permutation is ordered selection. Ordered selection. Here it is just okay. I'll write it here better. Permutation. It is ordered selection. What do you mean by ordered selection? Order is important. Suppose if I say ABC is one selection, then BAC is another selection, ordered. Here order is important. Who is coming first, who is coming next, that order is important. So if this type of selections are required, they are called as permutations. Now we are presently talking about only combinations, where order is not important. So let me say this one. So you are all clear about the concept of factorial. Suppose I say 5 factorial. Then I will multiply 5 with 4, go on decreasing up to 1. If you calculate this one, it is 5 4 is 20, 23 is 60, 60 to the 120. You can guess what will be 6 factorial. This 120, one more 6 will come, that is 720. So 6 factorial will be equal to 720. Let us come back to our work. This NCR is given by is equal to n factorial, it is n factorial, n minus r factorial, n minus r factorial, r factorial. You can write r factorial in the beginning, n minus r factorial in the next, that is not at all a problem because just we are multiplying. So n factorial by n minus r factorial into r factorial. This is the value for NCR. Now, how many will come in this case? 5C3 will be total number of selections, and that too unordered. Instead of every time saying unordered selections, ordered selections, we will simply say combinations, permutations. So without permutations and combinations, there is no counting. Back to the point, 5C3. How you will get the value of 5C3? 5 factorial divided by 5 minus 3 factorial, that is 2 factorial, into this 3 factorial. But I say don't go with this factorial notation. There is a simple way there is a shortcut of calculating 5C3. I will tell you that. First of all, let us simplify this way. So it is 5 into 4 into 3 into 2 into 1 divided by 2 into 1 into 3 into 2 into 1. You can catch one thing here, that this 3 factorial will be again present in this bigger number. So this will get cancelled. So leftover things are only this 5 and 4, 1 and 2. You can catch now what is the difference between these two, that is 2. So only 2 numbers will remain in the numerator, and this 2 factorial will be 2 into 1. So the shortcut is don't write this all unnecessarily. So 5 into 4 by 1 into 2 or 2 into 1. So it is 20 by 2, that's equal to 10. So how many selections will come? You can cross check now. If I say there are 5 objects A, B, C, D, E, and one is selection, for example ABC, second selection is ABC is not different from BAC, that's one and the same. A, C, D, like this. So totally 10 will come in this list. You can cross verify because it's a simple number 5 and 3 that you can write it. Now back to the point. If I have all 26 letters, that is A to Z, 26, I am selecting 4 from them. A, B, C, D, B, C, X, Y, A, C, Y, Z, like that. Then how many will be there? So simple, 26, we are selecting 4 and we are counting combinations. That's combination, that word C will be used here for combination. If you are talking about permutations, we will write P here, 26 P4 for permutations, 26 C4 for combination. So how much will be the value of this one? So simple, 26. In the denominator, 4 factorial will come. So we will write 1, 2, 3, 4. And in the numerator, we will write 26, 25. We will start decreasing from 26. How many are there in the denominator? Only that much factors we will write in the numerator. So 26, 25, 24, 23 over. This we are not simplifying. This is not required. As I said, 4 into 4 into 4, 1000 times is 4 to the power of 1000. It is enough. We are not calculating this one. Whenever the time arises, we will calculate it. And that too, we need not calculate. We are living in the modern world. We can calculate this 4 to the power of 1000 by computer. If computer fails, we will use supercomputer. So I hope you are very clear up to here. Let us cross verify with a still simpler number. We are having only 3 objects, ABC, and we are selecting 2 objects from that one. So this is 3, 2 objects are selected. This is N, this is R. One example is AB, one example is AC, another example is BC. Anything else remaining? Nothing. It is all exhausted. So only 3 will come. So that 3 is like this now. We are talking about combinations. So 3C2. 3C2 is equal to, if you want to write 2 factors here, that's fine. There is one more shortcut. This difference, if it is taken, then 3c. What is the difference here? That's 1. So these two will be equal. So this fine concept will be used when we are having bigger number here. Suppose I say what is 100c 98. One ordinary way is to write from 100. Okay, go on decreasing, and in 98 you write up to 98. But it is beautiful way. 100c 98. Difference is 2. So just go for 100c2. Then that will be equal to 100 into 99 divided by 2 into 1 over. So this is in between, I got it. Now here coming to two objects, it is 3c2. So 3c2 will match with 3c1. Why it is so simple? Out of 3 you are selecting 2. So what is the other part of the game? We are missing c here. We are missing b here. We are missing a here. So we can miss only these 3 elements. So this, for every 2 combination, there is a 1 combination correspondingly. So 3c2 is total number of 2 combinations. 3c1 is total number of 1 combinations. Therefore, the final point is 3c2 will be equal to 3c1. I hope you are very clear up to here regarding the combinations. Suppose the same ABC I take and I say I am talking about permutations with 2 objects. Then AB will be 1, BC will be 1, AC will be 1. But in continuation, this also gives rise to BA. Position is important. And this gives rise to CB. And this gives rise to CA. So now this will be 6. In this case, the notation is 3 permutations by taking 2 objects. So this is equal to, in the denominator we were writing 1 by 1 into 2 for combination. For permutation we will not write the denominator. Just we will write 2 factors starting from 3 going down. So 3 into, not 4, sorry, going down, 3, 2. So it's how much now? 6. That 6 is this 6. So here there is no shortcut here, 3 minus 2, something like that. If it is 100C98, you have to write from 100 up to 98 factors. 98 factors. So you have to leave 2, means 192 will not come, 3 onwards up to 100. So there is no shortcut in these permutations, keep in mind. Now tell me, if I take all of them, A, B, C, up to Z, only capital letters, I am selecting 3 objects and that too position is important. Then how many such selections will be there? Means I am talking about ordered selections. Order is important. Means I am talking about permutations. So how many permutations will come? 26, P, 3. 3 objects are selected. R is equal to 3. Okay. And N is equal to, this is total number of objects. So 26P3. What will be the value of 26P3? So simple, it is 26 into 25 into 24. This 3 is the total number of factors to be written. Starting from 26, reducing 1 by 1 like that. So it is 26P3. I hope you are clear. So let me end up the discussion of combinations here. Then the normal question arises in the mind, that is, I'll extend just for 2 or 3 minutes to settle one problem using combinations. It's very interesting problem now. Just if we learn how many combinations will be there and how many permutations will be there, it will not be so much, it will not give a so happy feeling for us unless and until we see some practical application of that one. Just I said, select a 3, 23 will come, 26 P3 will come. That will not be making any satisfaction for us. Let us really handle one problem of counting using the concept of combinations. If required, we will touch permutations, but let us make another video for that one. For permutations, let us limit our discussion to combinations. Suppose I am talking about binary sequences. Let me limit to, for example, 10 places. 1, 2, 3, 10 places. Every box should be filled with either 0 or 1, binary. That is only 2 digits will be allowed, binary 2. So one such selection or one such possible sequence is 1 0, 1 0, 0, and how many have come here? 3 plus 2, 5. Remaining all 5 ones I will write it. So it is a length 10, length 10 binary sequence. If I ask you how many will come in this list, it is so simple to do. There are 2 ways of filling this one. 0 or 1 will come in this position. 2 ways here, 2 ways here. So on up to 2. How many times? 10 times. So totally 2 to the power of 10. Totally 2 to the power of 10 sequences will come. So this is so simple concept, anybody can answer that one. Now if I write this question, that is very important question, how many binary sequences of length 10 are there in which there are exactly 4 ones. What do I mean about that? Exactly 4, neither less than 4 nor more than 4. This is not our binary sequence to be counted because it is already having 5 here and 2 here, 7 ones are there. So this sequence is not counted. So what type of sequences will come in this one? I will write some of the binary sequences here. So S is the total, it is the set of all binary sequences satisfying our condition. So first, so simple, I will write 4 ones. Then I will write 6 zeros, 3, 4, 5, 6. This is one element to be counted. So this is our required sequence, satisfying our condition of having exactly 4 ones. If it is having 3 ones, it is not counted. If it is having 2 ones, it is not counted. Similarly understood for 7 ones, 6 ones. Can you tell some more? I will write 1, 1, and in the last I will write 1, 1. 6 zeros I will adjust in this. 3, 3, 6. You can make a guess so many will come. 6 ones I will write first, and then I will write 4 ones. A very interesting question now, that is, how many will come in this set? Yes. How many will come in this set? Yes. Shall I wrap the question? Understood? Yes. How many? Whenever the word how many comes, we are counting how many. We are counting 1, 2, 3, how many. So it is a problem of counting. So I started my lecture with basics of counting. So we are at a very beginning level. It can be treated as the first lecture on counting problems. We will see some more if possible. We will have some more lectures on this one. It is the very basic lecture. So how many binary sequences will come? So the thing is, each and every binary sequence, you give some coding. Convert every binary sequence into some code. Once you code them, give a code for every sequence, coding will be easy for us to count. It should be some beautiful coding so that we will count it very easily. Now the coding is like this. 1, 2, 3, 4 ones, remaining zeros. I want to code this sequence in this way. 1, 2, 3, 4, over, game finished. What I am going to say here? I am putting 1 in the first 4 places. Remaining zeros are filled, that is required for 10 places, over. So what will be the code for this one? 1, 2, 1 to 1 to 9 10. Or so every binary sequence is now coded into a simple 4-number set. This is S1, this is S2. Is it possible to code everyone or not? So simple. What will be the code for this one? 1 is appearing in the last 4 places. So it will be 7, 8, 9, 10. Or this is S3. There is no need that this comes first or that comes first. There is no point in that one. So we are counting how many will come. So is this point understood by you? Yes. That every binary sequence we are converting into a code. That code is the positions at which 1 is appearing. This 4 here and this 1 here makes no sense, because first you are filling 4 here or first you are filling 4 here makes no sense. However, you are filling 4s. So 3, 1, 2, 4, 1, 2, 3, 4 all means the same. Are you catching the concept that this is a combination of 4 objects? Of 4 objects from, can you make a guess from how many? 10 objects, because totally 10 positions are there. So from 10 objects. So one selection or one combination, in our terminology combination, because it is a selection, order is not important, so it is a combination. We are saying we are collecting 4 objects from that, and totally there are 10 objects. So how many will come in this one? So simple. You can answer very easily. How many will come? 10 C4. 10 C4. What is the value of 10 C4? 10, 9, 8, 7. Better it is always to write the denominator 1, 2, 3, 4. Once you write the 4 numbers in the denominator, just to see, okay, still how many we have to write. You'll just see 4 are over, so 4 you have to. If you, so simple, you can write it over 10 C4. Let's simplify this one. How much it is? 8. This 8 gets cancelled. This 3 gets cancelled with 3 times. Okay. So it is 21 into 10. That is 210. 210 sequences. Is it possible for us to write all of them and see how many will come? No. So is this understood now?
Yes.
I hope you are clear about this one. So how many binary sequences will come with exactly 4 ones? Is 10 positions, because of length 10. 4 positions are selected. So 10 C4, that's equal to this one. Over. I hope you understood. Thanks for watching. Right?